Hello, today we're continuing with our series on electromagnetic radiation, looking at polarization. This is all part of a series where we're looking at what is light, the Poynting vector, the Fresnel equations, polarization, electromagnetic waves on metals, and waveguides. In the video What is Light, we considered an electromagnetic wave in the following way. We considered three axes, and we said that the wave propagated along the z-axis, this is the x-axis, and this is the y-axis, and we said that the electric field of the electromagnetic wave oscillates as a sine wave, or a cosine wave if you prefer, and the actual field is simply oscillating up and down in the x-axis. The whole wave is travelling along the z-axis at speed c, the speed of light, and that at right angles, in other words oscillating in the y direction, there is a B field, the magnetic field, and that is simply oscillating backwards and forwards in the y direction. And so you have the situation where the electric field oscillating in the x direction is perpendicular to the magnetic field which is oscillating in the y direction, and both of them are perpendicular to the actual direction of travel of the wave, which is in the z direction. And finally, of course, the E field is in phase with the B field, which means that they both reach a maximum and a minimum at the same time. Now, we have essentially considered the E field to oscillate in the x direction. So if we're looking at the wave head-on, so the wave is now coming towards us, then what we are seeing is an oscillating E field oscillating in the x direction like this. But there's no obligation for the E field to oscillate only in the x direction. That was how I chose to portray it, to explain it. But of course, the E field can oscillate in any direction it likes. You know, all of these lines, as many as you want to, can represent an oscillating E field. The wave is still travelling out of the paper towards us along the z-axis, and the associated B field for each of these E fields will be at right angles to it. But there's absolutely no reason why the wave, the electric field wave, should be, as it were, only in the x direction. It can be in any direction. And that is called unpolarized light. Just to be clear, although the E field can oscillate anywhere in this xy plane, it cannot have any component that is oscillating in the z direction, because the wave is moving in the z direction and the E and B fields are always perpendicular to the direction of movement. So the only way the E field can oscillate is in the xy plane. Now if we put that unpolarized light through a polarizer, what we will find is that we will get an oscillation only now in one direction. The direction will be the direction that we choose for the polarizer. In this case, I have chosen the x direction. All other oscillations will be wiped out. We will consider later how that happens in the video on the interaction of electromagnetic radiation with metals. So let's consider a polarizer which will produce, if it takes in unpolarized light and produces light that oscillates only in the vertical direction, I will indicate that the polarizer operates in that way with that kind of symbol. What that means is unpolarized light goes in, so let's draw unpolarized light goes in other words it's oscillating in all directions, and what comes out the other side is light that is oscillating only in the vertical direction. That will be my symbol for a polarizer having that effect. Now what is actually happening? Well, here is my polarizer, and let's take just one of the unpolarized oscillating fields. We'll take this one. So there we are. This is the E field that is coming into the polarizer. And what you can say is that what the polarizer does, I should just put a health warning, this is not strictly true. This is the classical mechanics explanation. Later in the autumn I will be doing a series on quantum mechanics where we'll actually talk about what really happens. But this is the explanation from a classical point of view. What you can say is that if this angle is theta, then the component of the E field, this is the E field E, the component of the E field in the vertical direction will be E cosine theta. Right, that's just straight trigonometry. There will also, of course, be a component of the E field in the horizontal direction, and that will be E sine theta. But the argument is that the horizontal component gets wiped out by the polarizer and only the vertical component is allowed through. Now in the video What is Light, we said that you can represent the E field as an oscillating field, and we did that with a sine wave. So we said that was E naught, that's the maximum amplitude of the wave, times the sine of kz minus omega t. And what we're now saying is that what actually gets through the polarizer is that value of E multiplied by the cosine of the angle between the vertical polarizer and whatever angle the E field happens to be oscillating in the unpolarized way. So what we're now going to say is that the component that gets through is E times the cosine of theta. Now in the video on pointing vectors, we said that the pointing vector, which we called S, and which is as it were an indicator of intensity, was equal to E squared divided by mu naught C. And if S is proportional to E squared, which it obviously is because these two are constants, we also showed that the average value of the pointing vector was proportional to E naught squared. But once this light has gone through the polarizer, only the vertical component survives, and the vertical component is E cosine theta. So we can rewrite that by saying that after polarization, the average value of the pointing vector will be proportional to E naught squared cosine theta squared. In other words, it's E naught cosine theta all squared. But this is going to be an average term because we're talking about the average value of the pointing vector. Remember that this is just one of the E fields that we were considering. The E field is oscillating in all directions, and for each one you have to take the cosine of theta for that particular oscillating E field. So when you get to here, you're talking about the average value of cosine theta squared. And the average value of cosine theta squared over a whole cycle is 1/2. And so you get that the pointing vector, or the average value of the pointing vector, which is a proxy for the intensity of the polarized light, is 1/2 the intensity of unpolarized light. So the intensity of unpolarized light on average is proportional to E naught squared. Once it's gone through the polarizer, it's E naught squared cosine theta squared. But the average of cosine theta squared, since theta will vary from 0 to 360 depending on which angle the E fields are oscillating, and they will be oscillating in all directions, the average value of cosine theta squared is 1/2. And so that's how you get that the average value of the pointing vector, which is the same as the intensity of the light that's gone through the polarizer, is E naught squared cosine theta squared, which is 1/2 what you had to start with. So now I'm going to consider unpolarized light, which oscillates in all directions, and I'm going to send it through a polarizer that will polarize in the vertical direction. So the light that emerges from this polarizer will, of course, be polarized wholly in the vertical direction. And as we've just shown, if the intensity of light, which is unpolarized, is I0, then the intensity of the light that comes through the polarizer will be a half I0. Now I'm going to send that light through another polarizer. This time it's going to be angled at 45 degrees. And the question is, what comes out the other side? Well, the same argument applies. You've got light that is coming vertically polarized, that's this light here, and it's hitting a polarizer which is at an angle theta. I said it was 45 degrees, but let's just keep it general for the moment. That is 45 degrees. What is the component of, this is the E field, remember the E field is oscillating now only in the vertical direction. What is the component of that E field on the polarizer? The answer, of course, is E cosine theta again. But this time there are no averages, because that's the only angle that matters, because all the light now, having come through the vertical polarizer, all the light is now vertically polarized. So all of it is going through a polarizer that is at an angle theta, and the component of all of that polarized light will be E times cosine theta. So consequently, the intensity, which you remember is in proportional to E squared, that means that the intensity of the light that goes through the second polarizer, I'll call that I2, is going to be proportional to the intensity of the light before it goes through the polarizer, and consequently it's going to be proportional to E squared cosine squared theta. So what we're saying is that whatever the intensity is of the radiation that is polarized, when it comes out the other side, the intensity will be reduced by a factor of cosine squared theta, where theta is the difference in the angle between the vertically polarized light and the angle of the polarizer. So in other words, the intensity that comes out this side will be the intensity beforehand, which was a half I0, times cosine theta squared. So we started off with intensity I0, unpolarized light. We put it through a polarizer. That gave us a half I0, because of course you've got light oscillating in all directions, and the net effect of all of that coming through a single polarizer is that you get half the intensity. You then send light which is only oscillating in the vertical direction through a polarizer which polarizes at an angle theta, and the intensity that comes through that is the intensity beforehand, which is a half I0, times cosine squared theta of that particular angle. I repeat, there is no averaging now, because there is only one angle in it, the difference between the polarization of the light and the angle of the polarizer. So let's explore what that angle means. Suppose that angle is equal to 90 degrees. That is to say that the light is oscillating vertically, but the polarizer is horizontal. Well, if theta is 90 degrees, the cosine of 90 degrees is 0. So cosine squared will be 0. Consequently, the intensity of light that comes through polarizer 2 will be 0, i.e. no light gets through. Suppose theta is 0 degrees. That is to say that the light is vertically polarized and the polarizer is vertically polarized, so they are both in the same direction. Well, if theta is 0, cosine theta is 1, cosine squared theta is 1, which means that I2 equals a half I0, which is the same intensity as the light beforehand. So in other words, all of the light gets through that polarizer if the polarizer is at the same angle as the polarization of the light. Another example, if theta is 60 degrees, then you need to take cosine 60 and square it, and that comes out to be cosine 60 squared is a quarter, and so I2, the light, the intensity of the light when it gets through that second polarizer will be a half times a quarter, which is 1/8. And if theta is 45 degrees, then you want the cosine of 45, which is 1 over root 2. Cosine squared is a half. That means the intensity of the light will be, well, it was half I0 to start with, and so it'll be half of that, which means that will be a quarter of I0. So in other words, the intensity of the radiation varies as the cosine squared of the angle between the polarization of the light and the angle of the polarizer. And this is all experimentally verifiable. You can take a light source, you can measure its intensity, you can put it through a single polarizer, and you can find that the intensity is reduced by half. You put it through a further polarizer at a different angle, and you find that the intensity varies as the cosine squared of the angle. And in particular, what that means is that if the polarizer is vertical and the light is vertical, there is no drop in intensity, 100% of that light gets through. If the polarizer is horizontal, whilst the oscillations of the light, of the polarized light, are vertical, then nothing gets through. And you can also do it for different angles. This is all experimentally verifiable. But as I said earlier, this is a classical explanation and it doesn't quite work. And the reason it doesn't quite work is that what we're saying is that the component of the E field, which passes through the second polarizer, is going to be the component, it's going to be the E field multiplied by the cosine of the angle between them. So in other words, what we said is if we've got vertically polarized light and you put it through a polarizer at an angle where that angle is theta, then the component of that E field in the direction of the polarizer is given by E cosine theta. Now what's wrong with that is that that suggests that the energy of the light after it's gone through the polarizer has gone down. And we know from basic quantum mechanics that light energy is carried in photons and that the energy of any given photon is equal to Planck's constant times the frequency of the light. Consequently, if the energy of the light reduces as it goes through the polarizer to the tune of cosine theta, of course will always be somewhere between 0 and 1, so you're always going to get a reduced value of the E field that you had beforehand. If that is true, that suggests that if the energy reduces, then since h is a constant, the frequency must reduce. And if that's the case, then the light will change colour. So that if, for example, you sent through monochromatic light that happened to be blue, and you sent it through the polarizer and the energy reduces, then what you will see coming out of the polarizer will be red light. But that is not true. If you take blue light and you shine it through a polarizer, if it gets through, it will be blue light. It does not change colour. So what we've got here is a classical explanation for the whole of the light, but it doesn't quite explain, because of this problem here, it doesn't quite explain how you can have a reduction in energy without a reduction in frequency. That's what we'll have to learn when we get on to quantum mechanics. And to give you a taster, the answer is that the energy is carried in photons, and the principle is quite simple. When the photons that are oscillating vertically, because the photons have been polarized, come up against this polarizer that is at an angle theta, they either get through or they don't get through. And the probability of them getting through is proportional to the cosine theta squared. Exactly what we calculated up here. That's the classical calculation, and it also turns out to be the quantum mechanical calculation, but for a different reason. Now we're talking about photons either do get through or they don't get through. And there is no way of telling whether any individual photon will get through. All you can do is to talk about the probability of a photon getting through. And this is the weirdness of quantum mechanics. All the photons in this vertically oscillating field are exactly the same. If it's monochromatic light, let's say it's blue light, all the photons will have exactly the same energy because the frequency for blue light is fixed, so the energy of the photon is fixed. They all have exactly the same energy. They are all oscillating vertically. They are all identical. And yet when they hit that polarizer, some will be reflected or absorbed, some will be transmitted. And there's no way of telling which will be which. That's the weirdness of quantum mechanics that we'll be coming on to later. Now I just want to remind you of what we did in the last video on Fresnel equations, where we said if you have a light beam coming from one medium to another, a dielectric medium, not a metal, to another, what you find is that some of the light will be reflected. We call that angle theta 1, and the angle of reflection was also theta 1, and some light is refracted or transmitted, and we call that angle theta 2. So the light is coming in here, it's being reflected here, and some of it is being refracted here. And we derived an equation in the Fresnel video which said that for the parallel component of the light, you'll recall that we said that this incident light will be unpolarized, so it will be oscillating. It will be oscillating in all directions, but all of those oscillations have to be perpendicular to the direction of the beam, so they all have to be in a plane which is, as it were, perpendicular to the direction of the beam, and that you can resolve those electric field oscillations into one that is coming out of the paper and one that is parallel to the paper. And when we did that, we did some calculations and worked out how you could relate the angles theta 1 and theta 2. And we said that for the parallel E field, the relationship of the reflected E field to the incident E field could be given by this equation, n2 cosine theta 1 minus n1 cosine theta 2 divided by n1 cosine theta 2 plus n2 cosine theta 1. And I just want to draw your attention to one interesting possibility here, which is what happens if the numerator is 0. That is to say, if n2 cos theta 1 equals n1 cos theta 2, then this term will become 0. And the whole of this will be 0. In other words, the reflected, the ratio of the reflected E field to the incident E field, this is the reflected E field, this is the incident E field, the ratio will be 0. That is to say, there will be no parallel component of the reflected E field, because in those circumstances this becomes 0. So the only E field that will get through will be the perpendicular E field, and that means the reflected light will be polarized because it's only now oscillating in the perpendicular direction. And for that to be true, these two terms have to be equal. So let's establish what that means. That means that n2 cosine theta 1 equals n1 cosine theta 2, which means that n1 divided by n2 is equal to cosine theta 1 divided by cosine theta 2. But now I remind you of Snell's law, which is essentially the law of refraction, that n1 sine theta 1 equals n2 sine theta 2. Just to confirm, we had done all this, so I'm assuming it, but n1 is the refractive index of medium 1. So this is medium 1, it has a refractive index n1. This is medium 2, it has a refractive index n2. And for refraction purposes, this is known as Snell's law, and it equates the two angles of incidence and the angle of refraction by the refractive indexes. So now we can say that from Snell's law, n1 over n2 is equal to sine theta 2 divided by sine theta 1. But n1 over n2 is also, in the specific conditions that we're talking about, cosine theta 1 over cosine theta 2. And the question is, what are the circumstances when that is true? Well, let me just draw you a little diagram. Here is a right angled triangle. I'm going to call this angle theta 1 and this angle theta 2, and this is 90 degrees. And the sides I'm going to mark x, y and z. That's the length of the three sides. Now, the cosine of theta 1 is equal to y over z. And the cosine of theta 2 is equal to x over z. And so the one divided by the other, which is essentially this term here, is simply going to be y over x. Now let's have a look at this same thing and look at the sine. The sine of theta 2 is equal to, sine of theta 2 is y over z. The sine of theta 1 is is x over z. And if you divide the two, which is what you need to do for this term here, you get y over x, the same thing. In other words, sine theta 2 over sine theta 1 equals cosine theta 1 over cosine theta 2 in the circumstances where theta 1 and theta 2 equal 90 degrees. For the obvious reason that this is a triangle which is made up of 180 degrees, one of the angles is a right angle, so the other two must add up to 90. So when theta 1 and theta 2 equals 90, you get this situation here where the numerator is 0, which means that the parallel component of the reflected wave becomes 0, which means only the perpendicular component goes through, which means that the reflected wave is polarized. When that happens, when theta 1 plus theta 2 is 90 degrees, then the situation is that the sine of theta 1 is equal to the cosine of theta 2. I can show that very simply. The sine of theta 1 is x over z. The cosine of theta 2 is x over z. So the sine of theta 1 is equal to the cosine of theta 2. Now if we just remember that Snell's law tells us that n1 sine theta 1 is equal to n2 sine theta 2. We've already dealt with that. We can now, for sine theta 1, we can put cosine theta 2, which means that n1, and instead of sine theta 1, we'll put cosine theta 2, is equal to n2 sine theta 2. Actually, I think I'll do it the other way round. If sine theta 1 is cosine theta 2, it's also true to say that the sine of theta 2 is equal to the cosine of theta 1. They are both equally true. And so now what I will do is I'll ignore what I just did there, and instead I will replace sine theta 2 by cosine theta 1. So now I'm going to get n1 sine theta 1 equals n2, and instead of sine theta 2 I'm going to put cosine theta 1. And now I can write that n2 over n1 is equal to the sine of theta 1 divided by the cosine of theta 1, and that's going to be equal to the tangent of theta 1, because sine divided by cosine of the same angle is simply the tangent. And just to remind you that all of this only applies when theta 1 plus theta 2 equals 90 degrees. That's the circumstances at which you get reflected polarized light. And that angle, which is the angle of incidence, is known as the Brewster angle. And you can find it by saying that the ratio of the two refractive indexes is equal to the tangent of the Brewster angle. So if you take the circumstances where light is going from air into glass, light comes in, is reflected, some of it is refracted. The refractive index for air will be 1, and the refractive index for glass is 1.5. Consequently, n2 over n1 is going to be obviously 1.5, and that is going to be the tangent of the Brewster angle, which is the incident angle here. And that gives you that the Brewster angle is 56 degrees. And incidentally, since theta 1 and theta 2 must add up to 90, that means that theta 2, or if you like, the angle of refraction, which I'll call theta t for transmission, must equal 34 degrees. So in this diagram here, this angle, the angle of incidence, theta 1, is 56 degrees. This angle, the angle of refraction, or the angle of transmission, is 34 degrees, and the two added together make 90 degrees. And in those circumstances, the light which is reflected is 100% polarized in the perpendicular direction. If we take the circumstances where light is going from air into water, for water the refractive index is 1.33, so n2 divided by n1 will now become 1.33, and that will lead to a Brewster angle of 53 degrees. So at 53 degrees, when the light is incident on the surface of the water, the reflected light, which of course will also be reflected at 53 degrees because the angle of reflection equals the angle of incidence, that reflected light will be 100% polarized. And one way you can test this is at the seaside. When the sun is shining on the sea at the right angle, if the sun is shining down here, and you're looking at the reflected light, the reflected glare coming off of the sea, that light will be 100% polarized at that angle. And if you are wearing Polaroid glasses, which will tend to be polarized in the opposite direction, those Polaroid glasses will completely take that glare on the sea away. So you won't see any reflected light at all, because the reflected light is polarized, and your polarized glasses tend to be polarized. They're designed this way at 90 degrees, so consequently it cuts out all the light. Now I'm going to show you that light which hits small dust particles in the air, those small dust particles must be less than 10 to the minus 6 meters. So they are very, very small, and the key thing here is that their diameter is of the order of the wavelength of the light that's hitting them. I'm going to show you that this light will be scattered, and in particular the light that is scattered at right angles to the incoming light will be 100% polarized. So let's just think about what that light is. We've already said that light oscillates. That's electromagnetic radiation. It is an oscillating E field, which oscillates in the, well, in this case I'm drawing it in the X direction, if this is the X direction here. And the question is, what happens if it encounters a charged particle, say an electron? Well, what does an electron do in an electric field? An electric field will provide a force on the electron, pushing the electron in the direction of the field. So when the field is in the up direction, that is in that half wavelength there, the field is pointing up, the electron will be accelerated up. When you get to this half of the cycle, the field is now pointing down, the electron will be accelerated down. This is a rapidly oscillating field, and consequently the electron will be oscillated up and down. We'll come on to this more when we deal with electromagnetic waves and metals. But essentially what is happening is you get an oscillating electric charge in all of these dust particles here. But we also know that oscillating electric charges themselves generate electromagnetic radiation. So consequently, the light that comes in here causes the charges in all of these dust particles to oscillate, and those oscillating charges, electrons, will themselves generate electromagnetic waves. So if this is the electron, and the electron is being oscillated up and down like that, it will generate an electromagnetic wave in all directions. So a wave will, as it were, spread out. We can represent that as the electromagnetic wave. It's essentially the principle of broadcasting. The electromagnetic wave goes out in all directions. But here's the important thing. Let's just consider the electromagnetic wave that goes out in that direction. The E field will oscillate perpendicular to the direction of travel of the wave. So the E field will be oscillating like that. The wave that goes out in that direction, the E field must oscillate perpendicular to the direction, so it must oscillate like that. And just let's draw one more, the E field that goes in that direction, the E field must oscillate perpendicular to it. So whichever direction the electromagnetic wave is radiating out from this oscillating charge, the associated E field will always be perpendicular to the direction of travel. So in principle what we've got is an electromagnetic wave coming in. That's this one here. It hits an electron and causes the electron to oscillate, and that oscillating electron generates another electromagnetic wave. So now I'm going to look at this incoming wave from underneath. Okay, so I'm now going to sit underneath and look at that wave which is coming towards me. So there it is, the wave is coming towards me. I'm underneath watching it come down. And which way is the E field oscillating? Well, answer, in all directions. It's an unpolarized beam. So the E fields can be oscillating in any direction. So let's just look at this in a little more detail. I'm still underneath. I'm still watching underneath. And there is the wave coming towards me. Let us now consider the E field that happens to be oscillating in that direction. That will generate another that will cause the electrons to oscillate in that direction, and that will generate electromagnetic radiation which will radiate off in all directions. I'm just going to consider the electromagnetic radiation that comes off in this direction because this is where I'm looking. And that's the equivalent, if we go back up here, to the radiation that's coming off at right angles. Okay? Because I'm actually underneath and I'm watching, so the light is coming out of the paper at me and I'm considering a wave that is travelling along the paper. In other words, at right angles to the direction of travel of the light. So that is essentially equivalent to this light being reflected, or sorry, scattered from the particles here. What do we know about the light that comes from here? The E field must be perpendicular to it. Well, okay, let's take another E field. Let's take this one. That E field will cause the electron to oscillate in all directions. Sorry, oscillate in this direction, but it will then radiate electromagnetic radiation in all directions. But let's consider the wave that happens to go along the plane of the paper. That too must oscillate in that direction because it has to be perpendicular to the direction of travel. What now about this one? Well, that's the E field of the incoming light, unpolarized. It causes the electron to oscillate in this direction. That generates electromagnetic radiation in all directions, but the radiation that comes along the plane of the paper must oscillate in that direction. In other words, all this unpolarized light, no matter which direction it is going, will cause electrons to oscillate in the direction of the E field. Those electrons will generate electromagnetic radiation, but the electromagnetic radiation that goes along the plane of the paper, in other words, perpendicular to the direction of the original light, will always be polarized, always be oscillating in the same direction. That means that it will be polarized. So consequently, we've shown that at 90 degrees, at a right angle, perpendicular, scattered, because what you've got is this light is causing the electrons to oscillate. That's generating electromagnetic radiation which goes off in all directions, but the electromagnetic radiation that comes out at 90 degrees is 100% polarized. Now, the amount of scattering that happens depends on the frequency of the light. So if you take sunlight, blue light is scattered more than red light. So if you've got the sun's light coming along like this, it is interacting with particles in the upper atmosphere, and more of the high frequency radiation is scattered than the low frequency. In other words, more of the at the violet end than at the red end is scattered. And the combination of a higher frequency scattering means that you will get more blue light scattered than red light. And that is why when you're standing on the ground, you look up at the sky and the sky is blue. By contrast, when the sun is very low in the sky, that is at sunset, here you are now looking at the sun on the horizon, and here is the light coming to you from the sun. Once again, the same principle happens. It's hitting particles in the upper atmosphere here, and that is going to scatter more of the high frequency away. So more of the blue light gets scattered away, which means that the light that is left is red. And so that's why the sky is blue during the day, because the light that is scattered tends to be at the higher frequency end. So you've got the greens and the blues and the violets all combining to form sky blue. And in the evening, all of those colours, the blues, are all being scattered out, and the only light that is left is at the red, orange, yellow end, and that's why at sunset you get the red, orange, yellow effects in the sky. All of that's down to what's called Rayleigh scattering. Finally, I want to look at what is called circularly polarized light. When we described the light or the electromagnetic radiation, we said that if we took directions X, Y and Z, for simplicity we said that we had the E field oscillating in the X direction, the B field oscillating in the Y direction, and the whole thing travelling in the Z direction. So if we look at it head on, that is to say we're looking along the Z axis at the light that is coming towards us, we would represent the E field as being in the X direction and the B field as being in the Y direction. Remember that the B field is C times smaller than the E field, so it is very, very small. and the B field is always perpendicular to the E field. But of course, as we've just said, in unpolarized light, the E field can oscillate in any direction in the XY plane. It cannot oscillate in any component of the Z plane because it must always be perpendicular to the direction of travel. So, for example, you could have, and we can draw this all on a circle, so we're still looking at the light coming towards us. We could have an E field like that with an associated B field like that. We could have an E field like that with an associated B field like that. We could have an E field oscillating like that with an associated B field like that. So unpolarized light, the E field can oscillate in any direction. The associated B field will always be perpendicular to it. So now thinking just about the E fields, forget about the B fields for a moment, we've got a whole load of E fields oscillating in all directions, and we can resolve all those, as we always can, along the X axis, which is the vertical axis, and the Y axis, which is the horizontal axis, and that says that the total E field of the unpolarized light will be equal to the component in the X direction, which is E naught X, times the sine of kz minus omega t. And that's going to be in the X direction, so I'm going to put a little hat there to show that that's a vector X, plus the component in the Y direction, sine kz minus omega t. But before I finish it, I'm just going to point out that this light doesn't have to be always in phase. There's no requirement that says that all the E vectors of the unpolarized light all have to be oscillating in phase with one another. In fact, they won't. So the component along the Y direction may well be out of phase with the component in the X direction. And for that, I'm going to put, as it were, a phase angle delta. And that is the component that's oscillating in the Y direction. What that means is if you take the E field oscillating, the components of the E field oscillating in the X direction, you might get something that looks like this. And if you take the component that's in the X direction, if you take the component that's oscillating in the Y direction, it doesn't have to be in phase, so it doesn't have to start there. It could start here. And the difference in angle is the angle delta. So let's just plot the X and Y components of the E field. This is the X component. Sorry, that's the X component because the X is vertical, isn't it? And Y is horizontal. So X and Y components, we will have a maximum, which is E naught X in this direction, and we'll have a maximum E naught Y in this direction. Again, no reason why they have to be the same. So consequently, this is the net E field, the combination of the EY and the EX components. Now, if delta is 0, that is to say the phase angle is 0, that means the two waves are in phase, which means that the components will both be oscillating in phase in the same way. So when the Y component is 0, the X component is 0. When the Y component is a maximum, the X component is a maximum, and consequently the E field is simply oscillating in this direction, like this, going from 0 to its maximum at an angle theta, which of course is determined by the relative size of the Y and the X components. And of course by, if you look at the total E field, which we'll call ET, Pythagoras tells us that ET squared is going to be E naught X squared plus E naught Y squared. That's just pure Pythagoras. But suppose delta is 90 degrees. They are exactly a quarter of a wavelength out of phase. Here is the x-axis, here is the y-axis. What that means is that when x is at a maximum, y will be 0. They're 90 degrees out of phase. So let's start. with E naught x at a maximum. That's going to be the E vector, because when x is at a maximum, y is 0, because they're 90 degrees out of phase. Okay, that's pretty clear. Now let's go 1/4 of a wavelength on, or if you like, 1/4 of a cycle on. 1/4 of a cycle on, the x field will have come down to 0, but the y field will have gone to a maximum. So this is the position when we start. This is the position 1/4 of a wavelength later. Now let's go on another quarter of a wavelength. Now this y field has reduced to 0, but the x field has now increased to a maximum in the other direction. Now let's go on another quarter of a wavelength. This will have gone back to 0 again, and the y field will have gone to a maximum in its direction. And what you will find then is that the E field is effectively moving around every cycle in what is shaped as an ellipse. And that is called elliptically polarized light. And the shape of the ellipse will be determined by the relative maximum values of the E field in the y and the x direction. In the event that the magnitude of the maximum value of the E field in the x direction is equal to the maximum value of the E field in the y direction, in the event that that happens, then what you will end up with is what's called circularly polarized light. The E field will just appear. It will start there, and then it will, in one cycle, appear to go round in one circle. As the relative values of the E field and the y field change, this is when the x and the y coordinates of the field are 90 degrees out of phase. That's called circularly polarized light. What that means is unpolarized light goes in, so let's draw unpolarized light goes in other words it's oscillating in all directions, and what comes out the other side is light that is oscillating only in the vertical direction. That will be my symbol for a polarizer having that effect. Now what is actually happening? Well, here is my polarizer, and let's take just one of the unpolarized oscillating fields. We'll take this one. So there we are. This is the E field that is coming into the polarizer. And what you can say is that what the polarizer does, I should just put a health warning, this is not strictly true. This is the classical mechanics explanation. Later in the autumn I will be doing a series on quantum mechanics where we'll actually talk about what really happens. But this is the explanation from a classical point of view. What you can say is that if this angle is theta, then the component of the E field, this is the E field E, the component of the E field in the vertical direction will be E cosine theta. Right, that's just straight trigonometry. There will also, of course, be a component of the E field in the horizontal direction, and that will be E sine theta. But the argument is that the horizontal component gets wiped out by the polarizer, and only the vertical component is allowed through. Now in the video What is Light, we said that you can represent the E field as an oscillating field, and we did that with a sine wave. So we said that was E naught, that's the maximum amplitude of the wave, times the sine of kz minus omega t. And what we're now saying is that what actually gets through the polarizer is that value of E multiplied by the cosine of the angle between the vertical polarizer and whatever angle the E field happens to be oscillating in the unpolarized way. So what we're now going to say is that the component that gets through is E times the cosine of theta. Now, in the video on pointing vectors, we said that the pointing vector, which we called S, and which is, as it were, an indicator of intensity, was equal to E squared divided by mu naught C. And if S is proportional to E squared, which it obviously is. Hello, today we're continuing with our series on electromagnetic radiation, looking at polarization. This is all part of a series where we're looking at what is light, the pointing vector, the Fresnel equations, polarization, electromagnetic waves on metals, and waveguides. In the video What is Light, we considered an electromagnetic wave in the following way. We considered three axes, and we said that the wave propagated along the z-axis. This is the x-axis, and this is the y-axis. And we said that the electric field of the electromagnetic wave oscillates as a sine wave, or a cosine wave if you prefer, and the actual field is simply oscillating up and down in the x-axis. The whole wave is travelling along the z-axis at speed c, the speed of light, and that at right angles, in other words oscillating in the y direction, there is a B field, the magnetic field, and that is simply oscillating backwards and forwards in the y direction. And so you have the situation where the electric field oscillating in the x direction is perpendicular to the magnetic field which is oscillating in the y direction, and both of them are perpendicular to the actual direction of travel of the wave, which is in the z direction. And finally, of course, the E field is in phase with the B field, which means that they both reach a maximum and a minimum at the same time. Now, we have essentially considered the E field to oscillate in the x direction. So if we're looking at the wave head-on, so the wave is now coming towards us, then what we are seeing is an oscillating E field oscillating in the x direction like this. But there's no obligation for the E field to oscillate only in the x direction. That was how I chose to portray it, to explain it. But of course, the E field can oscillate in any direction it likes. You know, all of these lines, as many as you want to, can represent an oscillating E field. The wave is still travelling out of the paper towards us along the z-axis, and the associated B field for each of these E fields will be at right angles to it. But there's absolutely no reason why the wave, the electric field wave, should be, as it were, only in the x direction. It can be in any direction. And that is called unpolarized light. Just to be clear, although the E field can oscillate anywhere in this xy plane, it cannot have any component that is oscillating in the z direction, because the wave is moving in the z direction and the E and B fields are always perpendicular to the direction of movement. So the only way the E field can oscillate is in the xy plane. Now, if we put that unpolarized light through a polarizer, what we will find is that we will get an oscillation only now in one direction. The direction will be the direction that we choose for the polarizer. In this case, I have chosen the x direction. All other oscillations will be wiped out. We will consider later how that happens in the video on the interaction of electromagnetic radiation with metals. So let's consider a polarizer which will produce, if it takes in unpolarized light and produces light that oscillates only in the vertical direction, I will indicate that the polarizer operates in that way with that kind of symbol.